let's continue on with our discussion of exponential functions, and in particular, the natural exponential function. So remember we talked about this right before break, where, pardon me, we did all those computations at the beginning and letting our n value get larger and larger and larger and larger, and noticing that even though they're getting bigger and bigger and bigger and bigger, these numbers are getting closer and closer to something, some value. So that value that gets closer and closer to is the value, pardon me, that we refer to as E. It's about 2.7, a little bit less than 3. It's an irrational number, which means that even though it looks like it repeats for this decimals that I put on here, it stops this pattern at the very next digit is not a 1. It's an irrational number, like pi is an irrational number, or like square root of 2 is an irrational number. It just means that when you write the decimal out, it never stops and it never repeats. So it's just kind of a random assortment of digits, if you will. When we put it for a base of an exponential function, this is what we refer to as the natural exponential function. And the idea behind why we call it a natural exponential function is because it comes from this particular type of computation. And we use it in lots of different applications that we'll see later on once we start talking about inverses of these functions today. All right, in particular, since the base is a number that's a little bit less than 3, in particular, the base is greater than 1, which means that our function's always going to be increasing all the time, right? We talked about exponential functions last time. And when the base is greater than 1, we know that it's an increasing function. So it has this basic shape here to the right we drew last time. The other properties are the same properties that all exponential functions have. The domain is all real numbers. The range is all positive numbers. It crosses the y-axis at 1. It never crosses the x-axis. And we have a horizontal asymptote at 0. All right, so this is just reviewing actually all exponential functions, if you will. Remember, all exponential functions have these properties. Whether or not it's increasing or decreasing depends on if your base is greater than 1 or your base is between 0 and 1. All right. So we're going to do more and more with exponential functions as we go along. Right now, let's just see if we can play around with some of the graphing ideas like we did last time with general exponential functions. So in this case, we've got the function y equals 1/2 e to the x plus 1 plus 2. And it's asking us to sketch a graph, and in particular, it wants to identify those transformations that we've talked about before and use a base graph and then use the transformations to sketch the graph of the function that's given. So, what transformations do you see? What different transformations do you see here? Yeah, it's going to be compressed which way? Vertically, right? It's going to get smashed down by a half because that 1/2 on the outside. What else do you see? The plus 2 tells you it's going to go up 2. Good. What else do you see? The plus 1. And what does that tell you? It goes left. Good. Because remember, for exponential functions, the exponent is the inside of the function, if you will, right? If you have f of x equals e to the x, when you plug a number in for x, it goes up in the exponent. So that's the inside of the function. Remember, if it's on the inside of the function, that it affects the input. So that's our horizontal shift there. All right, so we see 3 different pieces here. So if your base graph is y equals e to the x, then we see a vertical compression by a factor of a half. It's 1/2 as tall. We see a shift left 1 unit. and we see a shift up 1 unit. Or not 1 unit. Try that again. 2 units. So again, the 1/2 is on the outside of the function. The +2 is on the outside of the function. So that's what's affecting the outputs. That's why the 1/2 is a vertical compression, and the +2 is a vertical shift up. The +1 is on the inside, so it's affecting the inputs, which is where we get the left shift of 1. We okay with identifying those transformations? Is that okay? All right. So again, your basic shapes for exponential functions either go this way, right, or they go this way. They either go up and to the right or down and to the right, and they flatten out along the x-axis. Which one does e to the x do? Does it go up or does it go down? Up, right? Because the base is bigger than 1, so it has to go up, right? So your base graph is going to go this way and go up. Oh, hey, I kind of missed it there. Something like that. It goes up rather quickly. I told you that E is about 2.7-ish. So if we plug in 1 for the original graph, we would get 2.7. That's why I tried to make it cross there close to 3. When we put in 2, you get something that's a little bit bigger than 8. So it should be somewhere between 8 and 9 up there when we, pardon me, put in 2 for x. I don't really care about scale. I just want to care about basic shape here, right? So the big things that I'm looking for, there's basically 3 big things that I'm looking for when you're doing a base graph here. First one is that we've got that horizontal asymptote at 0. Second thing is that we cross the y-axis at 1. Third thing is that it's going up and to the right for this one. Okay. That's the basic shapes that you should think about in your mind when you're looking at exponential functions. Okay. There should be a horizontal asymptote. It should cross the y-axis at 1. And depending on the base, it either should go up and to the right or down to the right. Those are the kind of basic shapes. Not worrying about exactly where the points are. All right. First thing we notice is that we've got that vertical compression. So everything should be compressed by a half, right? In particular, this y-intercept here should get moved down to a half, right? And basically, as far as I'm concerned with drawing them, just make it look half as big, right? Does that change the horizontal asymptote, by the way, if it's half as tall? No, it stays exactly where it is, right? So again, you should have something that's getting close to the y-axis, close to the x-axis, goes through that half. It is half as tall-ish, right? Doesn't have to be perfect for my purposes. It just needs to illustrate that you really do understand that it's half as tall. What's the next transformation that we have? Shift left, right? In particular, this point here that's on the y-axis at 1/2 now should get moved over to about here, right? Does that change the horizontal asymptote again? Nope. And then again, basically make the same shape, but shift left 1. Now finally, we need to shift up 2. That one does change the horizontal asymptote. Where does it get moved to? If we're going to shift everything up 2, where does the horizontal asymptote get moved? It is at 2, right? It's now at 0. We're going to shift everything up 2. Our horizontal asymptote will be here at 2. This point again here is a half of a unit above that. Let's see if I can make that not so thick. And so again, we'll get close to that asymptote and go up and to the right. And it should have the same basic shape as the other one. That's our final graph. So again, we compressed it, we shifted it left, and then we shifted it up. These are things that we've already done before with transformations, right? It's just playing with a new graph to do the transformations. We're going to get another function today and another new graph, and we're going to play with the transformations of this as well. Is okay? Like I said, we're going to come back to doing some more properties with exponential functions, but we're first going to introduce the inverses of exponential functions, and those are logarithmic functions. So we'll start that today. Sorry. All right. Goodness gracious. All right, so new section today, talking about logarithmic functions. So we've already talked about that your exponential functions either, let me change my color back to black here, either go up and to the right or they go down and to the right this way, right? We've talked about those are your two basic shapes for exponential functions, right? Now, certainly it's a function, so it passes vertical line test, but it also passes horizontal line test, right? If I take any horizontal line, either it doesn't intersect the graph at all, or it intersects the graph in one point, right? That's what we mean by one-to-one, right? Distinct inputs give you distinct outputs. And these functions are either always going up or always going down. They don't turn around and make it not one-to-one anymore. So these pass the horizontal line test. And remember, that was our check of whether or not a function was one-to-one. And we wanted one-to-one because we wanted to be able to undo functions. And we had this whole discussion about, for example, the squaring function is not one-to-one. So if we want to talk about the square root function, to undo squaring, we have to cut it down to being just the positives. Right? We had that whole thing to make sure it was one-to-one. The whole reason why we want one-to-one functions is because we want to be able to undo them, or we want to make sure that it has an inverse function. That's why we want one-to-one. We want to make sure that the exponential function has an inverse function. So this is how we're going to define our logarithmic functions. Logarithmic functions are inverses of exponentials. All right? So when we want to talk about the log base A, where A is not equal to 1, but it is positive. Remember when we did exponential functions, we said that our base had to be bigger than 0 because we would get domain issues. We also didn't want a base equal to 1 because then you just got a flat line. Flat lines are not one-to-one. Okay? So that's why we have the exact same condition here. We want a positive real number that's not equal to 1. Then we define y equals, here's the notation. Y equals, we say log, we wrote the word log, base A, so this little subscript here, we say base A of x. So this is, again, a function. So we're going to get a log of a number. This means A to the y equals x. Okay. So let's see why these are inverses of each other, the way I've written this. Remember, inverses reverse the roles of x and y, right? Inputs become outputs, outputs become inputs, right? Notice here, here's my output, my y. Here's my output for my log function. That's the input up here for the exponential, right? The x is my input for the log. That's the output for the exponential. So they flip-flop them. Remember when we solved for when we found inverse functions, the first thing that you did was flip-flop your x and y and then solve for y? Remember doing those problems? I know you've slept since then, but we did those problems, right? You flip-flop your x and y and then solve for y again. It's exactly what we're doing here, right? These things have x and y flip-flopped. Notice that the big thing here, this is the big mystery for logarithms. This y is that exponent, right? That's all logarithms are. Logarithms are exponents. That's all they are. They sound mysterious. All we're looking for is an exponent. That's all that means, okay? So let's practice rewriting these things and then talk about solving some problems with some logarithms and getting some graphs. So this first part says express each of these exponential equations as an equivalent logarithmic equation. All right, so what do we mean by that? Basically, it just means, look at this statement that we have up here at the top of the screen. We have one that fits this form over here. We want to rewrite it so that it fits this form over here. That's all it's asking us to do. Okay? It says change the exponential equation into an equivalent logarithmic one. That's all it's asking us to do. Okay? All right. What's the base of the logarithm going to be? Well, what's the base of the exponential equation that you have? What's the base of the exponential function that's on the left-hand side of the equation? What's the base? 3. So that's going to be the base of the log. That's the first step. Pardon me. Thinking of this as an exponential function, what's your input and what's your output? If I think about that equation as actually putting something into an exponential function and getting something out, what's the input and what's the output? What will you be plugging into the exponential function? What number is getting plugged into the exponential function in this case? The 4, right? Remember the input is the exponent, right? So the 4 is the input. What's the output? What's the output? The 81, right? On what's on the right-hand side, correct? This 4 is the input. This 81 is the output for that exponential function, right? We just said that logarithms are inverses of exponentials, right? Inverses flip-flop inputs and outputs. So if this is the output for the exponential, what's that going to be for the logarithm? The input, right? So this will be your 81 here. This 4, you said was the input. So the input of the exponential becomes the output. Yeah. Another way to say this is the logarithm statement here is asking you a question. The question it's asking you is, what exponent, the outputs are exponents, logarithms are exponents. What exponent do you need on 3 to give you 81? That's what it's asking you. The exponent that you need is 4. Because 3 to the 4th is 81. That's what it's asking you. Okay? Let's look at the next one. Got it written a little bit differently. I've got cube root of 125 equals 5. That's certainly a true statement. Notice the problem, though, said convert the exponential equation into a logarithmic one. Right now, the way it's written, I don't really see an exponential equation, do I? But I do have a radical. And how can we rewrite radicals using exponents? Say again? To the 1/3. Good. Remember that whenever you have a fractional exponent, the denominator tells you what root to take, right? So if you had a square root, that would be a 1/2 power. A cube root is a 1/3 power. Fourth root is a 1/4 power, and so on. The denominator of a fractional exponent tells you what root to take. Okay? So now we have an exponential equation. What's the base? 125, right? The exponent is 1/3, and the output's a 5, right? Okay. So when I want to convert this to a log, what are we going to use for the base? The 125. Good. The 125 will be your base. What becomes the input for the log? The 5. Good. Yep. The 5 becomes the input. What becomes the output? The 1/3. Good. Remember, logarithms and exponentials are inverses of each other, right? So if you can identify the input and the output of one, flip them, and that gives you the input and the output of the other. That make sense? All right, what about the last one? This one it's got letters, but it shouldn't be that big of a difference here. We certainly have an exponential equation. What's the base of your exponential equation? B. So what's going to be the base of your logarithm? B. It's the same number, right? Whatever the base is for the exponential is the base for the log. What is the input of the log going to be? The Q. Good. The input for the log is the output for the exponential. That's the thing that's on the other side of the equal sign from the exponential statement, right? And then what's the output for the log? Z. Good. Questions on those? All right. Well, the next one say, do it the other way around. If we can go one way, we should be able to go another, right? Go the other. So do the exact same thing that I just talked about in the previous one. First, identify the base. What base are we going to use here? 7. Good. The base is going to be our 7, right? Now remember, these are inverses of each other. Inputs become outputs, outputs become inputs. If I want this to be an equivalent exponential equation, what should I be using for the exponent now? The 2. Remember, the outputs for logs are the exponents, right? So this 2 right here is the exponent that we want, right? And then what goes on the other side of the equal sign then? 49, and we certainly have a true statement, don't we? Does that make sense? All right, so you tell me how to write the next one then. So what's the 1/9 going to be? The base, good. Where's that going to go? You got exponential, good. Equals 27, good, exactly, yep. That's exactly right. The base is the same base, so the base of the logarithm is the base of the exponential. Outputs for logs are exponents, so this -3/2 goes up in the exponent. The inputs for the logs are the outputs of the exponential, so the 27 is going on the right-hand side. Questions on that one? By the way, you can check your answer. I mean, this is a true statement. You can check your answer here. And it doesn't hurt to check our answer to make sure that we're all on the same page with what these exponents mean. So let's just check and make sure I really do get 27 if you simplify the left-hand side. I'm just doing this as a check to make sure, and a review of exponents. Negative exponent tells you to do what? Flip it. Yep, right? Flip it upside down, correct? So instead of 1/9 to the 3/2, you'll have 9 to the 3/2, right? You agree? Okay. We just said a second ago that the denominator tells you what root to take, correct? So this would be square root of 9. The numerator tells you what power to take. So 9 to the 3/2 is square root of 9 cubed. You can also do it the other way around. You can do 9 cubed and then do the square root. But I think it's a lot easier to know what the square root of 9 is than know what the square root of 9 cubed is. What is square root of 9? 3. And 3 cubed is 27. Yeah. So we really did get 27. But like I said, you don't have, when you're doing these problems, you don't have to do the check that I'm doing here. I just wanted to make sure that we were all on the same page with those exponentials, right? The negative tells you, flip it upside down. The denominator tells you what root you're taking. The numerator tells you what power you're taking. So flip it to 9, take the square root to get 3, cube it to get 27. Does that make sense? You tell me how to write the next one. What would you get in this one? Okay, so the b is our base, right? Exponent is m equals w. Good, yeah, that's exactly right. And when we're talking about solving equations later, it'll be important to be able to do this rewriting that we're doing here. Questions on that? Is this okay so far? All right. All right, so let's talk a little bit about graphing these things. Again, not as worried about the scale as I am worried about what does the graph look like. Okay, same idea. So remember let's start with the exponentials. Remember for exponentials, we had two different forms. Let's just head. We had a form where the a was greater than 1, and we had a form for when the a was between 0 and 1, right? For exponentials, let's start there. For an exponential function, which way did the graph go? Did it go up or down if it's bigger than 1? Up, right? And it's down for the other case, correct? So our basic shape, not worried about scale. I don't care about the vertical scale here, okay? Just care about the shape, all right? We had that horizontal asymptote, went through the y-intercept at 1, and kept going up, right? This is a to the x, correct? Right? The other one went the other way. Same basic shape, just flipped, if you will. All right. The reason why I'm starting this is I need to start somewhere to get the graphs of the logs, rather than putting in a bunch of numbers. I could do this by putting in a bunch of numbers, but that seems like overkill. Remember that when you graph inverse functions, you do that reflection about the line y equals x. Okay. Remember that's the reflecting line? But again, our big principle is that inverses, we flip-flop x's and y's, okay? So let's find a point on the inverse function by flip-flopping x and y's. What's the coordinates of this point right here? What's the coordinates of your y-intercept? 0, 1. If we flip, we get 1, 0, right? So remember, inverses are flip-flopping x's and y's. We get the point 1, 0 on the graph of the inverse. Okay. Horizontal, let's do the horizontal asymptote next. What's the equation of the horizontal asymptote? We said the horizontal asymptote to the x-axis. What's the equation of that line? Y equals 0, right? If you flip-flop x's and y's, y equals 0 becomes x equals 0, which is what kind of a line? Vertical, right? It goes up and down. So our inverse function is going to have a vertical asymptote of the y-axis. Notice that looks like a reflection, doesn't it? Remember when we reflect about the line y equals x? If you come in at a 45-degree angle, you're going to go out at a 45-degree angle. Right? And now we should be able to get the rest of the graph. This one's going to go up. This one's also going to go up. We just have the mirror image idea. So we've got this vertical asymptote this way, and then it'll peel off that way. So this will be log base A of x. So our final graph, our graph of the inverse, our graph of log base A of x, when A is greater than 1, is this blue one that I have on the screen here. And it should look like a mirror image of the a to the x function across the y equals x. Okay. Let's do the other one. Again, I'll put in the line y equals x here, just for a guiding line. And actually draw the line y equals x as opposed to whatever heck I was just drawing there a second ago. And if I can change the color of my pen, do it that way. Again, same idea. Where does the point 0, 1 get flipped to? 1, 0, good. Still goes here. The horizontal asymptote becomes what kind of asymptote? Vertical. And we'll come, and again, we're going to reflect this, so it's going to go this way and go like so. Notice that log functions have the same type of property that the corresponding exponential does. If the a is bigger than 1, it's increasing. If the a is between 0 and 1, it's decreasing. Same idea. All right. So let's see if we can write some properties down. All right, so what do we see for the domain? Well, remember that inverses, again, interchange the roles of x's and y's. So the domain of the inverse function corresponds to what for the original function? The domain corresponds to the x value, the domain, right? The range of the domain is the x, the domain of the inverse corresponds to the range of the original, right? So that's the flip-flopping of the x's and y's. What's the range of any exponential function always? Zero to infinity. So the domain for any logarithmic function is going to be 0 to infinity, and we can see that from the graph, can't we? Does this graph go to the left side? No. How about the range? The range of the inverse corresponds to what for the original function? The range of the inverse corresponds to the, well, the range are the y values, but as far as the original function goes, the range of the inverse is the, just as far as the words go, domain of the inverse corresponds to the Right, we just said the domain of the inverse corresponds to the range of the original. So range of the inverse corresponds to the domain. Yeah. What is the domain of any exponential function? What's the domain of any exponential function? So what's the range going to be for the logarithms? Negative infinity to infinity. And can we see that from the graphs again? Yeah. All right. How about the x-intercept? What do you notice for an x-intercept for the log functions? Good. And remember that corresponds to the y-intercept of the original, right? Oops, 1, 0. You said 1, 0, and I wrote it backwards. Right? The x-intercept on the inverse has to be the y-intercept of the original. Right? You flip-flop them? What about y-intercept then for your log functions? There aren't any. Good, because there weren't any x-intercepts for the original. What do we say the equation of the vertical asymptote is? X equals 0, good. When is it increasing? When does the function go up? Yeah, so x is going to infinity, but looking at the two graphs we have above here, yeah, when the base is greater than 1, right? If your a value is greater than 1, and it decreases if your a value is in between 0 and 1, just like it did for the exponential. All right. So let's see if we can put some of this stuff in action for doing some transformations, just like we did with the, pardon me, the exponential functions. We've got log base 2 of x plus 2 minus 1. So what do you think you might use for your base graph here? Yeah, log base 2 of x, right? Our base graph here will be y equals log base 2 of x. So is that going to go up or down? Is it increasing or decreasing? Yeah, it's increasing because of the 2, right? It's bigger than 1. So again, we're going to cross the x-axis at 1. We'll have the vertical asymptote, that is the y-axis, and we will go up and to the right this way. If you wanted to get a couple of extra points here to help with your graph, you could. You could plug in 2 for x, you can plug in 4 for x, and see what you get out. If you plug in 2 for x, remember, logarithms are exponents. It's what exponent do you need on the base to get the input? So this is asking you, what exponent do you need on 2 to give you 2? 1, right? So log base 2 of 2 is just 1. And notice that is exactly where I drew the graph through, isn't it? The 0.21. Okay. What would happen if I plugged in 4? What power do I need on 2 to give me 4? And you would tell me 2, right? Because 2 squared is 4. So this would be 2. And you can see also that I drew it through that point. Let me do one more. What if you plugged in a half? What exponent do I need to put on 2 to give me 1/2? -1, right? Because the negative exponent is flipped upside down, right? This is flipped upside down. And notice that is where I put the graph through, isn't it? You can get some extra points by doing that to get your graph to look a little bit better. All right. Past that, what transformations do you see? Yeah, shift left 2 and down 1. Good. The shift left 2, does that move your vertical asymptote? Yeah, sure does, doesn't it? The shifting left moves the vertical ones now, doesn't it? Okay. So we're going to get a vertical asymptote here at -2. Change my color, maybe. We'll get that vertical asymptote at -2. The point at the x-intercept at 1 will move to -1, and we'll get a graph that looks like so. And then we need to shift it down 1. Does that change your vertical asymptote now when we shift it down 1? No. Vertical asymptote stays in the same spot. And we'll go up into the right this way. And get that graph. I didn't make that graph very good, did I? It's all right. Questions on that? Just using the same shapes that I were doing. Sorry, using the same transformations, but with just a different shape of function. We agree? So what happens in the other one, then the next one? What are we going to use for our base graph here? So our base graph will be y equals log base 1/3 of x. So is that going to go up or down? Because? Not because of the negative. I was just looking for the base graph. Yeah, it's less than 1, right? The base is less than 1, so that tells me it's decreasing, right? So it's going to go this way. Now what transformations do you see? Yeah, there's a shift right 1. What else? Shift up 2. What else do you see? Yeah, the reflection, which way? Yeah, it flips it top bottom, right? It's on the outside, so it affects the y's. So we'll have a reflection about the x-axis. So we have 3 transformations in this case. We've got a reflection and a shift and a shift. So the reflection will send it looking like that. Flips it upside down, right? That's what negative signs do on the outside. It flips them upside down. Right? Flips it top to bottom. Then we shift it right. 1. That'll move your vertical asymptote over to 1. And make it go this way. And then finally, we will shift it up 2, we said. So flip it upside down. That was the red one. Move it right 1. That's the blue one. And then up 2. That's that sparkly one that you can't see the sparkles very well because it's small. Yes. Say that again. Did we reflect twice? Like we need the negative should just flip it once, right? Like it did. So our original graph is this one. It's going down this way. That's the original. So the flip is just the red one. Why isn't the original one going like normally? Because our base is between 0 and 1. So when the base is between, so it's decreasing instead. Okay. Yeah. You're right. If the base were greater than 1, it was like it would have reflected it twice. You're exactly right. Yeah. Yeah, it turns out that when you've got the base that's less between 0 and 1, it basically is the original just kind of flipped upside down. Yeah. Other questions on that one? Okay. Let's do the first one here, and then we'll do a couple more with another one with the domain next time. But there's some new problems that can come up with log functions that we haven't talked about before, and that's with domain. So remember, the domain of any log function is positive numbers. I cannot put in 0, I cannot put in negative numbers for a logarithmic function. So much like what we do for square root, when you're looking at the domain of a log function, you're looking for when the inside is positive. For square roots, it could also be 0. For the logs, it can't. So in this one, it just wants us to solve an inequality. So we would solve the inequality 9 minus 4x is greater than 0. So we would subtract our 9. What happens when you divide both sides by -4? What happens to the inequality? The sign flips. Good. So we get x is less than -9/4. So our interval would be -infinity up to -9/4. So for any of these that are domains, this is exactly what you're going to do. It's just like what we did for square roots. Right? Yes. Oh, thank you. Yep. Thank you. That better? Yeah. Thanks. So it's just like what we did for square roots, except that it cannot be equal to 0. It has to be strictly greater than 0. So what inequality would you set up in this next one? What inequality would you set up to start the next one? Okay, so you would have to set the inside needs to be what? Well, you're right, you need to factor it, but what do we need to have on the other side? Yeah, it needs to be strictly greater than 0, right? We need to set up that inequality. And this looks like problems we did before, doesn't it? This looks like those polynomial inequalities, doesn't it? Okay, so we would factor, and exactly like Kyle said, it factors as x minus 1 times, x minus 4 times x plus 1. So we would make our sign chart. What makes that equal to 0? 4 and -1. We would pick test points, and I know we're almost out of time. Actually, I guess we are out of time. If you pick test points, you'll get positive, negative, positive. You can check that. What are we looking for in this case? Positives. So we would have -infinity to -1 and 4 to infinity. So again, when you're asked to find the domain, this is just like problems you've done before. In particular, it looks a lot like what we did for square roots, right? The only thing that's different when we're doing this in square roots is you don't have the equal to sign. All right. We'll do more of these next time, as well as to get into new stuff. So have a good one. We'll see you on Wednesday.